So now that we've sort of spent some time looking at the two variable case, let's for a moment consider larger systems. Okay, and we're going to restrict ourselves to studying linear systems once again. I will give you a handful of examples of what a nonlinear system um, looks like, but again, solving those, we might get to it week 10, we might not. It will just sort of depend on the speed that we kind of go through all of this. So the first thing that I want to expose you to um, is a linear equation in n variables. Okay, and what a linear equation in n variables is it sort of generalizes what we've been talking about, right? You might have a linear equation in one variable, right? Say 5x plus 1 equals 3, right? Or you might have a linear equation in two variables, right? Something like this guy here, okay? The general form, right, of these things, they look like this. Say a sub 1, x sub 1 plus a sub 2, x sub 2 plus say a sub n minus 1, x sub n minus 1 plus say a n xn, that equals c, right? And we have the following, right? We have that a1 through an and c are real numbers, right? And the x1, x2, all the way through xn are variables, right? If we were, say, using two variables, right, we might call x1 x and x2 y, right? If we were using three variables, we might use x, y, and z for x1, x2, and x3. In the case of four variables, we might use x, y, z, and w, right? Once you go more than that, it kind of starts getting a little hectic with all the letters, so you just switch to numbered subscripts, but we won't be working with larger systems than four, okay? And so you can build systems out of these equations, right? And as we've said, you can build, linear and nonlinear. Let me give you two quick examples of nonlinear systems. The system, or the tools we have aren't going to be great for solving these, but they are a little bit fun to try and, puzzle through. So I know that, we're in a very busy part of the quarter, but if for some reason you really want to take a break and try and solve these, well, go right ahead, be my guest. Okay, so here's two nonlinear equations, okay? And I guess you could put them in a system, but I would not be able to tell you out the top of my head if this as a system had any solutions. So there's two things that make it so this first guy is not a linear equation, right? For one, x is squared, right? And for two, z is square rooted. And in our archetype form, all of these are to the first power, okay? For the second one, I guess I should write that a little bit cleaner. That's 6, it's in the wrong color. It should be 6x sub 3, right? This is great, but unfortunate here we have two of our variables multiplied together, which is bad, okay? And so now that we've kind of seen this, done some, groundwork theoretically, let's sort of look at our first system in three variables, okay? And I'll talk you through one of our goals with how we're going to solve these. Minus 2y minus z equals 1. We have minus x plus 3y plus 3z equals 4. And 2x minus 3y plus z equals 10. Okay, so this is, in a standard form, right? We have three equations in three variables. And here's what our actual goal is going to be in solving these, okay? We want to transform it, and we'll build up the methods for how to do this, to something that looks more like this, okay? Our first equation stays the same. We want to find a way to build an equivalent system that looks like this, okay? This is what we call triangular form, okay? And this is why it's so nice, right? You can use back substitution on this triangular form to get the answers almost immediately, right? Watch this. We can read off z equals 3 right here, right? So I guess we'll go to green for this. We have that z equals 3, right? We can use our value of z in equation 2, right? So that gives us that y plus 2 times z, which we know is equal to 3, equals 5, okay? Rearranging this, we're going to get that y equals negative 1, okay? Now that we have a value for z and y, we can plug both of those into our first equation and read out our value for x, okay? So we're going to get that x is minus 2 times minus 1 minus 3 equals 1, right? When I rearrange this, we're going to get that x equals 2, okay? So we can read off our ordered pair. That's our solution, right? We have 2, negative 1, 3, right? And I invite you, go ahead, definitely check this solution in this equation, right? And in this equation, it turns out, these two are equivalent, right? So any ordered triplet that will solve this will also solve this, right? This is why we're interested in converting into this triangular form, right? Where, you've got, sort of triangle right there. And I guess you could also consider, sort of like hidden 0x's and 0y's right there, okay? So now the question is, right, how do we convert into triangular form, okay? And there's three operations that are allowed, okay? So here's how we keep a system equivalent. So we can do the following operations. We can do the following operations without like changing the ordered triplet that will solve our system, okay? So here's our first one, okay? We can add a non-zero multiple of one equation to another, okay? We can multiply an equation by a non-zero constant, and we can interchange the positions, right, or switch the order of our equations, right? And so this third one, basically, it would come into account, right, if we were, say, given an equation, or say equation 1 just stated z equals 5. Well, it would be really nice if that one could be our third equation, right? Because that's what triangular form has. It has just the, z equals whatever on the bottom. And this one is saying that that's a perfectly valid move. Now, what I want you to notice is that for these 1 and 2, this is precisely the elimination method from solving our two variable systems, right? That's why we leaned so heavily on that in the last lecture, was because those are the methods that we're going to use to translate an equation into our triangular form, okay? So let's do an example of this. Let's say we have the following system: x minus 2y plus 3z equals 1, and x plus 2y minus z equals 13, and 3x plus 2y minus 5z equals 3. While I label these, I do want to point out that I am aware that my crossing of z's is inconsistent, and I am sorry. I have tried for years to pick one method, and it has yet to work. So for the most part, right now I'm not crossing them, but every once in a while a crossed z might slip into our work. Okay, so let's solve this. Okay, so if I'm attempting to write this in triangular form, okay, the first thing I need to do is get rid of these x's, right? Because we need to have 0x in both of these, entries here, and then eventually a 0y here. Okay, so the first thing that we're interested in doing. And what we're going to do is we're going to multiply equation 1 by a non-zero multiple and then add it to equation 2. Okay, I know that this will get a little bit tricky, but I think once you kind of get some practice in it, will become a little bit more comfortable and feel less awkward. Okay, so the first thing that we're going to do here is we're going to copy down the equation that we want to go, or that we want one of the factors to go away, right? So that's equation 2, x plus 2y minus z equals 13, okay? And so what should we multiply this by in order to cancel with this x? Well, that would be -1. So I'll move these over here for a little bit more room, okay? This is equation 2. We want to do -1 times equation 1. Okay, and what that's going to do is it's going to give us -x plus 2y, looks like minus 3z equals -1. Okay, and so what we're going to do is now add these. Okay, and when we add them, we're going to get 0x's, which is what we want. We're going to get 4y. We're going to get minus 4z. We're going to be 12. Okay, and what we're going to do is we're going to rename this as equation 2. Okay, and the reason we can do that is it says right here we can add a non-zero multiple of one equation to the other. We added -1 times equation 1 to equation 2, and then use that to redefine equation 2, right? Let's do the same thing with equation 3. Okay, copy down equation 3, label it, okay? And then we need to multiply equation 1 by, it would seem to be -3, right? Because when we do that, okay, looks like we're going to get -3x plus 6y, looks like minus 9z, that's going to equal -3, okay? And labeling that, that's -3 times equation 1. When we add these together, looks like we're going to get 0x's, which is perfect, that's exactly what we want. We're going to get 8y's minus 14z's, and 0 for our constant term, okay? And this is our new equation 3, okay? And so let's collect this information, okay? Our original equation was x minus 2y plus 3z equals 1. Our new version for number 2, so we have 4y plus 4z, I guess minus 4z, equals 12. And then our third one, I believe it was 8y minus 14z equals 0. Okay. So here's what we're going to do next. Okay. We have these gone, and the next thing we want is to get this one away. Okay. So we know we want to mess with equation 3. So the first thing we're going to do is write equation 3, which is 8y minus 14z equals 0. Okay. And we want to use equation 2 to manipulate this, right? Notice that if we used equation 1 to manipulate this, we would introduce an extra factor of x, which is not what we want, right? We want this to stay with 0 x's, okay? And it would seem to me that if I want to get my coefficient of y to be negative 8, I should multiply it by negative 2 times equation 2. And we're going to get minus 8y, looks like plus 8z equals minus 24. Okay. And when we add this through, looks like we're going to get minus 6z equals minus 24. Okay. So what we did after that was we redefined this. It won't quite fit there. So this is what our system has become. We still have our first one, equals 1. We have 4y minus 4z equals 12. We have minus 6z equals minus 24. Okay, but I want to make one change to this. And that one change is that I want to multiply each of these rows by a constant. And the reason I want to do that is I want to get rid of these leading coefficients. Okay, and everything has worked out so nicely, right? All of these are divisible by 4, and both of those are divisible by 6, right? So that's going to give us the system x minus 2y plus 3z equals 1. Looks like that's going to be y minus z equals 3, and z equals 4. Okay. So now we want to go through the process of back substituting, right? So we know that z equals 4. Or I guess I'll do this in purple, right? We have that z equals 4. That's going to tell us that y minus 4 equals 3, right? Or rather, y equals 7, okay? Then we're going to have that x minus 2 times 7 plus 3 times 4 equals 1. Okay, we move this 12 over, we move this negative 14 over, and we're going to get that x equals 3. Okay, and that's going to leave us with the final solution of x equals 3, y equals 7, and z equals 4. So I know that these examples are a little bit long, and have lots of little processes, right? And so maybe this will be a consolation. Maybe not. Let's do some theory instead, right? So we have the number of solutions to any linear system, okay? So this is going to generalize the thing that we talked about in the last part, right? So we have, for a system of linear equations, once again, exactly one of the following is true, okay? And these should not surprise you, okay? So we have that the system has exactly one solution, which is often the thing that we're hoping for, right? We have that the system has no solutions, Once again, those are called inconsistent systems. Or we have option 3, the system has infinitely many solutions. Okay. I'm going to draw a picture of what this looks like in the 3 system case, or the 3 equation case. Most of what we'll be doing will be with 3 equations in 3 variables. On the homework, there might be a couple with 4, but it's all going to go through the same process. I'm not going to draw the 4-dimensional case, as I personally cannot draw in 4 dimensions. I'm going to struggle to draw in 3 dimensions, as you'll see. But let's take a look at this. Okay, so here's what I want you to realize. An equation with 3 variables is the equation for a plane. Okay, a plane in 3-dimensional space. And so what that means is that what we're looking for is the intersection of 3 planes. Okay, so in this case, right, we might have these 3 planes like this. Okay, where you may have that line there, that line there, and then there's also a green. I guess the green line would also be under that. So I'll draw that too, right? All 3 of these planes, right, intersect at this single point, right? This system has exactly 1 solution. Okay. Our second option is if we have, say, 3 planes. We'll have them sort of oriented like this, such that the planes meet along a line. Okay, so maybe we have the purple one doing something like that. Sure. I have my notes from last quarter up for this, and that looks much better than last quarter's, which is probably saying something. But so this is our dependent system, right? This has infinitely many solutions. All of the solutions lie along this vertical line right here. Okay. And here's our third one. I guess these are out of order from that example, aren't they? I guess I'll move them around after. Let's say we have a situation like this. We have our red plane slanting that way. We have our purple plane slanting this way. Sure. And then, maybe we have our green plane going across like this, right? We might have an intersection here, right, where the red plane and the green plane meet. We might have an intersection here where the green plane and the purple plane meet. We might have an intersection here where the purple plane and the red plane meet, right? But there's no point where all 3 of these planes meet each other at the same time in the same way there was in this situation, right? Hence we call this an inconsistent system, okay? Like I said, these are not in the order that they're listed above, so I'll move them around, okay? So let's give ourselves an example of each of these, okay? So let's solve this system right here. We might have x plus 2y minus 2z. See, that's why I cross my z's, because they look a lot like 2's sometimes. We have 2x plus 2y minus z equals 6. And we have 3x plus 4y minus 3z equals 5. Okay. And so what we want to do with this, guys, we want to march through the same steps that we had before, right? And one by one, sort of start to knock out these elements, okay? So let's start by, trying to reduce equation 2, right? So we'll copy equation 2 back down. 2x plus 2y minus z equals 6, right? That's equation 2. And it looks like I want to multiply equation 1 by negative 2, right? It's going to give me a negative 2x. Looks like minus 4y plus 4z equals negative 2. And when I add these, looks like I'm going to get 0x, which is what we want, minus 2y plus 3z equals 4. Okay. Let's do the same for equation 3. Copy it down. 3x plus 4y minus 3z equals 5. Equation 3. And equation 1, well, it looks like it should be multiplied by negative 3, right? Going to give us minus 3x minus 6y, looks like plus 6z equals negative 3, okay? Adding these together, we're going to get, looks like 0x minus 2y plus 3z equals 2, okay? So here's what we're going to get, right? Copying this down, x, I'm going to have plus 2y. I'm going to go up here and fix that because that doesn't look like a very good plus. Minus 2z equals 1. Here we're going to have minus 2y plus 3z equals 4. Minus 2y plus 3z equals 2. Okay. And here I immediately see a problem. Okay. And that is what happens when we try to reduce this, right? So here's what's going to happen, right? If we're trying to change equation 3, we're going to multiply equation 1 by negative 1, right? That's going to give us a plus 2y here, to minus 3y there. And then when I add them, right, this is what's going to happen. Our first two equations are going to stay the same. So I guess I'll copy and paste those. Okay. But that was a minus. That was a plus. But then what's going to happen for the second one? We're going to get 0y plus 0z. It looks like that's going to come out to, since that one becomes negative, it's going to come out to negative 2. Okay. But this last equation, right, this says that 0 equals negative 2, which is like definitely false, right? So that means our equation is inconsistent and we have no solution, okay? Let's go ahead and look at one more of these, okay? And this is what our system is going to look like, okay? So we have x minus y plus 5z equals negative 2. We have 2x plus y plus 4z equals 2. We have 2x plus 4y minus 2z equals 8. Okay. So let's just sort of, move along the ways that we have been. Let's look at equation 2 plus y plus 4z equals 2. And we want to use equation 1 to get rid of this, right? And so we should multiply that by, it looks like, negative 2. Okay, so multiplying equation 2 by negative 2, or rather, multiplying equation 1 by negative 2, it's going to come out to looks like negative 2x plus 2y minus 10z equals 4. What do we get when we add these? We have 0 x's, it looks like 3 y's, it's going to look like negative 6 z's with an output of 6. Okay, and so that's going to redefine our equation 2. Next, we want to mess with equation 3, so we'll copy it down. 4y minus 2z equals 8. Okay, and notice we actually want to multiply negative 2 times equation 1 again, right? Sometimes that's what is best, right? So we're going to have the same thing, negative 2x plus 2y minus 10z equals 4. And when we add these, what do we get? 0 x's, which is great, 6 y's minus 12 z's. It looks like an output of 12. Okay, so let's copy this down. We have x minus y plus 5z equals negative 2. Copying down our new equation 2, we have 3y minus 6z equals 6. We have 6y minus 12z equals 12. Okay, and we do still have a rather interesting situation here. Okay, and that is that these look pretty similar. If I were to write the 1 and 12, they would look a lot more similar, right? This sort of resembles what we had before where, equation 3, at least the right-hand side, or the left-hand side of it, right? This is 2 times that, okay? But unlike the previous one, these also differ by a factor of 2 as well, right? Which means when I multiply equation 2 by negative 2, and I add it to equation 3, what we're going to get is 0 equals 0, right? Which is perfectly true, right? Once again, I'm just going to copy this top one. And you're more than welcome to go through the details. I definitely encourage it, right? Show this, like multiply this guy by negative 2 and try adding it to this guy, right? You're going to get 0 equals 0. But this is a true statement, but it provides virtually no useful information, right? So essentially what we now have is we have a system of 2 equations and 3 variables. We have x minus y plus 5z equals 2. And then our second equation is 3y minus 6z equals 6. Okay, but what I am going to do right here is let's multiply this whole row by 1 over 3, right? That's going to give us 3y minus 2z equals 2, right? So now what we want to do is we want to solve these guys in terms of x and y, okay? The equation that handled our z value, you can imagine it sort of blew up a little bit, right? We have one of these dependent systems, right? And so we're now seeking to solve everything in terms of some variable t, right? Just like we did in the 2 variable case. And to do that, we need to solve for x and y, okay? We're going to use the substitution method here, right? This is one of the places where it's super useful because we know that y is 2 minus 2z, right? So that means that x minus 2 minus 2z plus 5z equals 2, right? This should be plus, sorry, but then that should be in brackets, okay? So when we expand this out, we're going to get x plus 3z minus 2 equals 2. or x equals negative 3z. Okay, so now we have our values of x and y in terms of z, right? Just like in the last lecture, or the last part, we had our value of y in terms of x, okay? So now we're going to go through sort of the same idea. So we're going to say let z equal t for some real number t, okay? And then this is what our solution is, right? We can just read this off, right? X is minus 3 times whatever z is. Y is 2 plus 2 times whatever z is. And well, z is just t, okay? And these categorize our solutions, right? This is a line in three-dimensional space, okay? And for any value that you would plug into t, you could get a valid solution, okay? In fact, we can form a little box, right? We have minus 3t, 2 plus 2t, and t. So we can say negative 1, we're going to get 3, it's going to come out to 0, and negative 1. We could say t equals 0, right? Well, it looks like we're going to get 0, 2, and 0. What if we plugged in 10, right? We could get negative 30. That one looks like it's going to come out to 22, and then 10, right? All of these are valid solutions. Plug them into the system. Make sure they work. Don't just trust my word for it. Make sure this process makes sense, okay? So that's where we're going to leave it for this week. Next week, we're going to sort of look at these structures called matrices and sort of how they make this process a little bit cleaner and allow us to kind of glean a little bit more information out of these systems, okay? So I will see you guys next week.